Hey kiddos, we're looking at our sixth review segment. This is based on rectangular approximation methods, RAM, integrals as area, integral props, and the fundamental theorem of calculus. First off, we got RAM stuff, and in all of these I think we're given tables for us to kind of work with. So let's go through these. So a car comes to a stop 5 seconds after slamming on the brakes, and the velocities are recorded. Total distance. So we're talking about the area of velocity, which is total distance. It says to use appropriate approximations. It doesn't tell me which one to use. So I could do right, left, midpoint, trapezoidal, anything I want for this. For this one, I might choose left rectangles, and I just might choose that because, I don't know, kind of makes sense to me. The big idea here is that we're going to use the left coordinate of each rectangle for the height, and we're going to use the width of each interval as our bases. So each of these intervals is broken up into a 1 second segment. And if I start from the left side, we've got a 1 width and an 88 height. We've got a 1 width and a 60 height. That's that one. We've got a 1 width and a 40 height. We've got a 1 width and a 25 height. We've got a 1 width and a 10 height. That would be left rectangles, whatever that comes out to be as an answer. So that'd be 88 and 60 is going to be 148, 188, 208, 213, 223. I could also do right rectangles. I'm kind of annoyed that I used blue for that one. And right rectangles would be the same thing, but starting with the right side. A lot of you like starting all the way on the right, so we could do that. And you'd have 1 times 0 plus 1 times 10 plus 1 times 25 plus 1 times 40 plus 1 times 60. And we don't go all the way to 88 because we're just using the right side of each rectangle. And when I do that, I've got 100, 125, 135. So that's a vastly different number using left or right rectangles. But both of them are viable estimates. Using MRAM, we have to be able to have something that we can break things into midpoints. I don't have any data for like the 0.5s. So one of the ways that we could try to do this is to look at wider intervals. We're going from 0 to 5. I don't know that we're going to get a nice clean thing, because if I try to do intervals that are too long, and by that I mean 2 units long, I'd have to have the 6th point. And if I try to do intervals that are 1 long, I don't have enough information. We can't use MRAM for this one because we don't have intervals that let us do so. And then finally, I could use trapezoidal. And I could break this into those same subintervals going from 0 to 1, 1 to 2, 2 to 3, and so on. And in doing that, we've got to use the trapezoidal area formula. So that would be a half. Base 1 would be 88. Base 2 would be 60. And the height would be the width of the interval, so that'd be 1. And then we end up with a half. 60 plus 40, those are our 2 bases. And then we end up with a half. 40 plus 25. And then we end up with a half. 25 plus 10. Make sure that you show those ones also. Don't be lazy like me. And then a half. 10 plus 0 times 1. Okay. So that'd be 44 and 30 would be 74. Plus 30 is going to be 104, 124, 144, 144, 146, 146 and a half, 156, 158 and a half, 159, 164, and then we got another 5, so that's going to be 1,674. And that works for us. You might also notice that ends up being exactly in the middle of those two, because what we're really doing is taking an average. Also another reasonable estimate. Okay, number 2. We've got a golf course. The caretaker draws power lines 10 feet apart. Okay, so that means that each of these intervals is going to be 10. How many square feet must be purchased? Okay. First off, we're going to use midpoint rectangles. That's something we didn't get to do in the last one. So I'm going to call MRAM. And the midpoints mean that we need a height in the middle of an interval. So for each of these, we have to have an interval that's wide enough that we can have a height that's in the middle. So my first interval might be 20 wide, because that's really 2 intervals. And that would be 28. Then another 20 wide times 62, and another 20 wide times 55, and another 20 wide times 30. Then the caretaker uses left rectangles. If I were to use LRAMs, and if I broke this back up into intervals of 10, that'd be starting with a 0 point. So 0 times 10 plus 28 times 10 plus 50 times 10 plus 62 times 10 plus 60 times 10 plus 55 times 10 plus 51 times 10 plus 30 times 10. And then using right rectangles, that'd be starting on the right side. So we got 3 times 10 plus 30 times 10. Then if we keep going, we got, sorry, that should be times 10. There we go. Then we got 51 times 10, then 55 times 10, and then 60 times 10, and then 62 times 10, and then 50 times 10, then 28 times 10. And then finally trapezoids. I'm going to do these as bigger trapezoids so I don't have as many things to do. I'll use the same intervals I used for the midpoint, so that'll give us 4 different trapezoids. So for the first trapezoid, it's going to be 1/2. Base 1 would be 0. Base 2 would be 50. And then that's times a width of 20. Then we're going to have 1/2. Base 1 would be 50. Base 2 would be 60. And we'd have a width of 20. And then I'd have 1/2. And now we're going from 60 to 51. 60 plus 51 with a width of 20. And then 51 to 3 plus 1/2. 51 plus 3 times 20. That's all 4 ways. For number 3, we got Roger deciding to run a marathon, and Jeff rides him on a bicycle and clocks him every 15 minutes. The data is summarized below. Assuming Roger's speed is always decreasing, estimate the distance that Roger ran in the first half hour and the entire race using trapezoids. Okay, so for the first half hour, we're looking just at these pieces, and I might use trapezoids based on each part of this. So for the first part, we're talking about 1/2. Base 1 would be 12. Base 2 would be 11. and then that's times a interval width of 15. For the next part, we'd be talking about 1/2. Base 1 is 11. Base 2 is 10. And the interval width here would be 15 also. That's part A. Part B would be whatever we got in part A, and then keep going. So maybe 1/2, and then we got 10 plus 10, and that's going to be times a width of 15. And then 1/2, 10 plus 8 with a width of 15, and 1/2, 8 plus 7 times a width of 15, and then 1/2, 0 plus 7 times a width of 15. That would be our area, in other words, the total distance that's traveled given the amount that we have here. Part 2, we're looking at definite integrals as area. I believe we did this, actually even the same assignment earlier in the year, and what we're really doing is looking at this in terms of the geometry here. We know that the integral from a to b of f of, in this case, t dt, is the area under the curve. We also know we have some negative areas and positive areas based on being above or below the x-axis, and using geometry is a great way for us to deal with this. All right, first of all, we've got area from 4 to 4. That's an area under a point. That would be 0. Area from 0 to 1, that's this guy right here. That would be 2. Area from 1 to 3, that would be this triangle. 2 by 2 is 4, times 1/2 is 2. 0 to 3, well, we did 0 to 1 and 1 to 3. We can combine those to get 4. 3 to 6, that's 1, 2, 3, 4, 5, 6. That's this triangle down below. It's got a height of 1 and a width of 3, which would be an area of 3, but it's below the x-axis, so we got negative 3 over 2. From 6 to 3, when we flip the integral, we flip the sign. 3 to 6 was negative, so 6 to 3 would be positive 3 over 2. 0 to 6, I've got to add all these pieces together. So we've got 0 to 3, which is 4. 3 to 6, which is minus 3 over 2. When I add those, that's 4 plus negative 1.5 is going to be 2.5. From 6 to 10, that's my circle part. My radius is going to be 2. Pi r squared times 1/2 would end up being 4 pi times 1/2, which is 2 pi. 10 to 6, we're flipping the bounds, negative 2 pi. 0 to 10, we're going to add everything up. I'm going to start with 0 to 6, which is 2.5, and I'm going to add 6 to 10, which is 2 pi. So 2.5 plus 2 pi. For number 11, we're flipping the bounds again. That's going to be minus 2.5 minus 2 pi. From negative 1 to 0, we're talking about this trapezoid in here, which is made up of a rectangle and a triangle. The triangle is going to have an area of 1. The rectangle's got an area of 2, so we're talking about 3 for the whole thing. From negative 3 to 0, we've got this triangle, this triangle, this rectangle. The rectangle is going to be 4. Triangle up top is going to be 1. Then this is going to be 1 by 2, 3, 4, 5, 6. 1 by 6 is going to be an area of 3. So going from negative 3 to 0 would be 3, 7, 9, 10, 11. 0 to negative 3 would be negative 11. Negative 4 to negative 3, that's going to be negative 1/2 because we're below the x-axis. From negative 4 to 0 is going to be negative 1/2 plus positive 11, which is going to be 10.5. From negative 4 to 10, so it's adding the positive and negative parts of our graph, is going to be really adding these two pieces together, and that's going to give us 13 plus 2 pi. Absolute value of 0 to 10 is going to be the same thing because that's a positive number. So, except I used the wrong one. I want to use 10 for this. So that's 2.5 plus 2 pi. 19 is different. We're talking about the absolute value of the areas. So this part would be flipped up. This part would be flipped up as well. And instead of doing minus a half and minus 3 over 2, we're going to do plus a half and plus 3 over 2. Which is going to take us to a different value. So it'd be plus 2 to get back to 0, and then plus another 2 would be 6.5 plus 2 pi. The absolute value from 4 to 10, I think we had that one already. Although maybe not. I'm not seeing it. It may be there. So we're talking about from 1, 2, 3, 4. This is going to have an area of 1, and then to 10 is going to have an area of 2 pi. But we'd actually want the negative version because we're just doing the absolute value of the whole thing. So we're really looking at the negative 1 plus 2 pi, which is positive, so the absolute value doesn't change it. And I'm totally misreading this because that's not actually 4, that's negative 4. Durr. So it's asking for that whole thing again, and this was here. So that would again be 13 plus 2 pi, which is positive. And then we're looking at from 10 to negative 4, which would be, this is a fun one. So interestingly, I did number 19 wrong because I added this rectangle in here too. And I really just wanted to add this 3 over 2 part. I want to add that twice. So it should be 5.5, not 6.5. Okay, back to this one. So this one is asking us to start with the area from negative 4 to 10. 13 plus 2 pi. But now we've got to account for this being positive and this being positive. That's plus 2 to get back to 0, and then plus another 2. So that'd be 17 plus 2 pi. And then it's going to reverse it. So negative 17 minus 2 pi. Next up, we got some integral properties. Again, this is from quite a while ago this time. And we're going to do what we can to try to make sense of this. All right, first thing is if we've got two separate integrals and we're adding them together as we are for 22, we can just add the areas together. So that's 18 plus 5 is 23. For 23, going from negative 2 to 5 of f plus g minus h, we're working this one in here. So 18 plus 5 minus negative 11 is going to be 34. For problem 24, we're flipping these around. We're looking for g of x. And 4 times g of x is going to be 4 times as tall. That's going to be 4 times the area, which is going to be 20. But we want the flipped version, so that's going to be negative 20. For number 25, we're moving this whole thing up 2. Another way to think about this is that we're doing this separately as the g of x part, and then also the integral from negative 2 to 5 of 2 dx, which is the area of a line horizontal with a height of 2. In other words, a rectangle that has a height of 2 and a width of 3. So it would be g of x plus 6, and g of x is 5. 5 plus 6 is 11. For number 26, we're doing the same thing, but with f of x, and we're minusing 6. So this would be trying to deal with the width of 7 there. Oh man, that also makes me realize that I did the previous problem wrong in terms of the width, because negative 2 to 5 is not 3, it's actually 7 wide. So it's not plus 6, it's plus 14. 5 plus 14 is not 11, it's 19. Same thing going on here, though. There we've got a height of negative 6 and a width of 7. So that would be 42 negative. And for f of x, that looks like 18, and then minus 42. 18 minus 40 is going to be negative 22. Minus 2 more would be negative 24. For number 27, we're going from 0 to 7 of h of x minus 2. And this one's actually really sneaky. This one's really sneaky because you have to know that this means that this graph needs to go to the right 2. So this is actually 2 units to the right of where it should be. And this would be equivalent to saying negative 2 to 5. You might see where this is going, of h of x. Because if we minus 2 on the inside, that would be moving the whole thing, including the bounds, to the right 2 units. And this one we happen to know is negative 11. We can do the same thing here. This would be to the left 2. So this is to the left 2 of where it should be. That would take us to negative 2 to 5, bada bing, of g of x dx, which is the same thing as 5. 5 to 8 of f of x dx. So we know 2 to 8. I'm going to write this as the integral from negative 2 to 8. That's the whole thing of f of x is equal to the integral from negative 2 to 5 of f of x dx plus question mark, where that's what we're finding here. So we've got 0 is equal to negative 2 to 5 is going to be 5 plus question mark. That's going to be negative 5. And for number 30, we've got f of x minus 3 and then plus 3. Okay, I'm going to deal with plus 3 at the end first. That moves the whole graph up 3. We've got an interval of 7. So I'm going to have a plus 21 going on here. 3 to the right means this would also be negative 2 to 5 of f of x. And negative 2 to 5 of f of x is going to be 18. 18 plus 21 is going to be the very lovely 39. Now apparently we're thinking about integrals as something. Oh, it's a function. I'm going to put negative 5 there just so we don't lose it. And here we've got a function. We've got this graph below. F of 0 would mean that we're looking at the integral from 0 to 0, which would be 0. F of 2 means we're doing f of 2 minus big F of 2 minus big F of 0. In other words, the area from 0 to 2, that looks like a quarter circle with radius 2. So the circle would be 4 pi, quarter circle would be just pi. F of 4 would be 0 to 4, so that's a semicircle. That would be 2 pi. F of 6, this is going to have an area of negative 2. We'd be going from 0 to 6. That would be 2 pi minus 2. F of negative 1. Now we're going backwards, so this is going to be kind of interesting. So this would be the integral from 0 to negative 1. You might recognize as that's going to be the negative version of this. This would have an area of 1 because it's a 1 by 2 triangle. Therefore, f of negative 1 would be negative 1. F of negative 2, we're going to go a step further. And we've got 1 and 2, which would be 3. But going in the wrong direction is going to be negative 3. F of negative 3. We're going to add some other fun stuff going on here because this is split into 2 pieces, each of width. See what I did there? Is going to be a half unit wide by 2 tall. So that would be a half, and this would be a negative a half. And when we do that, those cancel each other out, leaving us with the same value of negative 3. F of negative 4, we're going to add one more piece onto this. This is going to be negative 1. So we end up with 2, but we're going in the wrong direction. This is going to be negative 2. F prime of 4. What that's asking us to do is to take the derivative of the antiderivative of 0 to x f of t dt, and then plug in 4. Hopefully we know that the derivative of an integral is just going to be that function. And if we're plugging in 4, that's asking for the height of this graph when x equals 4. So we move this up a little bit. There we go. So 1, 2, 3, 4 has a height of 0. Is a bigger thing. That means that we're looking for the height of the graph, not the area for f primes. So big F prime of 2 is going to have a height of 2. Big F prime of 6 is going to have a height of negative 2. And big F prime of negative 3, 1, 2, 3, is going to be at negative 2 as well. All right, we're going to do some FTC stuff. And confirming user calculator is going to be fn int. The big idea here is that if we have the integral from a to b of some function f of x, we might even call this f prime of x if you want to think about this as a derivative, and that's going to be equal to f of b minus f of a. So plugging these values in. Starting with number 1, the antiderivative of 3x is going to be 3x squared over 2. Plugging in 1 and 0 is going to be 3 over 2 minus 0, which is 3 over 2. For number 2, the antiderivative of x squared minus 5 is going to, of x minus 5 is going to be x squared over 2 minus 5x, going from negative 2 to 3. And that's going to end up being 9 over 2 minus 15, and minus 4 over 2 is 2, minus 10. 9 over 2 minus 15 is going to be minus 10.5. Minus 2 minus 10 is going to be minus negative 8. And we end up with negative 2.5 for that one. For number 3, we're going from negative 1 to 4. X squared is going to be x cubed over 3 plus 2x squared over 2 minus 1x, going from negative 1 to 4. That would end up being 64 over 3 plus 32 over 2 minus 4 minus negative 1 over 3 plus 2 over 2 plus 1, and whatever that comes out when you add those things together. For number 4, we don't have a way to deal with this directly unless we use some u substitution, which, why not? U is equal to 2x minus 5. That means that dx is going to be du over 2. In other words, we're going to end up dividing this whole thing by 2 in the end. So we'd end up with u squared, which is going to be, 1/2 u squared, u to the third over 3. So we end up with a 1 over 6, 2x minus 5 to the third, going from 0 to 2. Minus 5 to the third would be negative 125. I don't know why I'm doing 0 first. I'll plug in the 2 first. We get 1/6. 2 times 2 is 4, minus 5 is negative 1. Negative 1 to the third is negative 1. Now we'll do the 0. So we got 1/6. Negative 5 to the third is negative 125. When you combine those, you will get your answer. For the next one, I'm going to rewrite this as the integral from 2 to 3 of 4x to the negative 2 plus 1 dx. 4x to the negative 2 is going to become 4x to the negative 1 divided by negative 1. In other words, negative 4 over x to the 1. Then plus a 1x going from 3 to 2. That would be negative 4 over 3 plus 3. And then minus negative 4 over 2, which is negative 2, plus 2, which is 0. Ooh, that's kind of nice. So just negative 4/3 plus 3. For number 6, I'm going to do the same thing and rewrite this as the integral from negative 2 to negative 1 of x minus x to the negative 2. And when I do that, we get x squared over 2, and then the minus is going to change to a plus. 1 over x evaluated at negative 2 and negative 1. So negative 1 squared is going to be 1 over 2 plus negative 1. And then minus negative 2 squared is going to be 4 over 2, which is 2, plus 1 over negative 2 is minus a half. For number 7, I'm going to do some manipulation first. We're going from 1 to 9. And I'm going to rewrite this as x over x to the 1/2. That's what square root is. Minus 2 over x to the 1/2. Which is going to be this integral from 1 to 9 of x. I'm going to minus these two powers. That's to the 1/2. And then minus 2 to the negative x, to the negative 1/2. Then when we integrate, we're going to have x to the 2/3. I'm going to add 1 to a half, and that's dividing, so I'm going to multiply that by 2/3. Sorry, x to the 3 over 2. Whew, I'm losing it today. And then that's going to be minus, it's going to be divided by a half, so times 2. So that's going to be 4x to the positive a half. Plug in 9 and plug in 1. I'm going to leave that part because I'm out of room and let you figure that part on your own. For number 8, we're looking at the integral from negative 2 to 2 of x to the 1/3, which is going to be x to the 4/3 divided by 4/3 is 3/4, x to the 4/3 at 2 and negative 2. For number 9, we've got more fractional exponents going on here. And when I add 1 to each of these, so that's going to be t to the 5/3 times 3/5, and t to the 4/3 times 3/4, evaluated at 1 and 0. 0 for both these would be 0. 1 for both these would be 1. That's really going to be 3/5 minus 3/4. For number 10, we've got the absolute value going on. I'm actually going to sketch a graph of this. I think that's going to be the easiest way for us to do this. And absolute value is going to have a 0 value at 2. It's going to go up to 2. And then I only need one more piece. So we're talking about these triangles, the first of which has an area of 2, the second of which has an area of 1, and that's going to be 3. Cosine of x from negative pi over 2 to pi over 2. And looking at this, what we're going to do is do the antiderivative, so we get sine of x, and evaluated at pi over 2 and negative pi over 2. At pi over 2, sine of pi over 2 is going to be 1. Sine of negative pi over 2 is negative 1. We get 2 as an answer. For number 12, we got 2x minus sine x, and that's going to end up being 2x squared over 2, which is x squared, plus cosine of x from 0 to pi. So that would be pi squared, and cosine of pi is minus 1. And minus 0 plus cosine of 0 is 1. Pi squared minus 1 is going to be pi squared minus 2. And the last page. This is going to be using FTC deriv, the fundamental theorem of calculus, and to take the derivatives of the following functions. The big thing we have to remember here is the chain rule whenever we see something like this. So we're doing the derivative of this guy, which is going to be x squared plus 1 to the 20 times the derivative of x, which is just 1. For the next one, we're doing the derivative of the antiderivative, and we're doing this with the chain rule. So we're going to have x cubed plus 1 times the derivative of what we're plugging in, which is just 1. For the next one, we're doing the same thing. We're doing 1 over 1 plus x to the 4th times the derivative of what we're plugging in, which is 1. And for the next one, we're doing the same thing. It's cosine, except we're plugging in an x squared this time. So it'd be an x squared squared, because it's t squared. And we're multiplying by the derivative of x squared, which is 2x. The reason that we don't use the bottom numbers is because if you took the derivative after integrating, it would be a number, and derivative of a constant is 0. All right, same thing going on here. I'm going to do tan inverse of e to the 5x squared cubed plus 2 e to the 5x squared plus 1 times the derivative of e to the 5x squared, which is e to the 5x squared times 10x, minus, now we have to do minus, we have something in the bottom, tan inverse of sine cubed of x plus 2 sine x plus 1 multiplied by the derivative of sine x, which is cosine of x. The thing to remember is the chain rule. And most of the time we're just going to plug in 1. In cases like this, we plug in a lot of other stuff too.